with the Eightfold Path in Buddhism. It mentions some ways like right action, right speech, right thought, etc. for an enlightening and a fulfilling life. Not similar, but we have an eightfold way in particle physics also, where we organize the hadrons into certain geometrical patterns so that it will become easier to identify new particles and understand their properties. So in today's lecture, we'll be seeing eightfold way in particle physics. So let's start. So before learning about eightfold way, we need to get introduced to a new type of quantum number called as isospin quantum number. So now we are already familiar with the baryon number, strangeness quantum number, right? So this isospin quantum number, it was introduced by Heisenberg. This is to explain the symmetries of these particles. So these symmetry operations are mathematically supported by group theory, which is out of scope in this lecture. So let's consider some particles which we are familiar with. We have neutron and proton. So as we know, neutron and proton, they have similar mass, similar spin, and they differ only in their charge. Right, neutrons, they have zero charge, and protons, they are positively charged. And together, we call them as nucleons. Similarly, we have pions. Pions, they are particles, pi. We have pi plus, pi 0, pi minus, similarly sigma particles, etc. So these particles, we call them as multiplets because they differ in a single property. Right, you have a pi particle, a pion, and these three pions, they just vary only in their charge. All the three pions, they have almost similar mass, similar spin. They vary only in their charge. So this kind of groups, we call them as multiplets. So neutron and proton, they are doublets. Because you are having two properties, two particles with similar properties, just different charges. Similarly, for pions and sigma particles, we call them as triplets. So any particle which exists in multiple states, you call them as multiplets. Fine. Now let's define isospin. So before isospin, we'll see what a hypercharge is. Hypercharge is denoted as Y is equal to B. That is a baryon number, strangeness quantum number, charm number, bottom number, and top number. Now with the particles that we are familiar with, we won't be considering these two numbers because we know for protons, neutrons, and the hyperons that we know, they all possess a baryon number and a strangeness quantum number. There are no charged bottom and top quarks in the particles that we are familiar with. Okay, so we can define isospin quantum number Iz as Iz equal to Q. Q is the electric charge of the particle minus Y, that is the hypercharge, by 2. So normally when we consider hypercharge for the particles that we are familiar with, we take hypercharge Y is equal to B plus S. So isospin quantum number is Q minus Y by 2. So let's see again the particles that we know. We have neutron with a charge 0. So using this equation, we can find the isospin quantum number of neutron as Iz is equal to charge Q is 0 minus Y is equal to B plus S, that is baryon number. Baryon number is 1 for a neutron and strangeness quantum number is 0 for a neutron divided by 2, or we have Iz is equal to minus 1 by 2 for a neutron. Similarly, let's see for a proton, protons are having charge plus 1. Fine. So instead of 0, we have the charge as plus 1. Plus 1 minus half, which means isospin quantum number for a proton is plus half. So we can consider neutron and proton being a fundamental particle called as a nucleon, one with a positive isospin and the other with a negative isospin. So this is the significance of the isospin quantum number. So isospin quantum number defines different particles which belongs to a particular multiplet. Similarly, we can find the isospin quantum number for all the pion, sigma particles. So we can understand that they are fundamentally a single particle with different isospin quantum numbers. Now, based on this isospin, we are going to see what is called as a super multiplet. So, super multiplet is a combination of different multiplets. We have already seen what a multiplet is. Multiplets, they will be having same baryon number, spin, strangeness number, but different isospin quantum number. And a super multiplet is a combination of certain multiplets which have the same spin and baryon number. Now, this super multiplets is what we are going to arrange it as an eightfold way of particle physics. So, this concept was actually proposed by Murray-Gell-Mann and Yuval Neeman independently. So, Murray-Gell-Mann, he is considered as a person who is totally fascinated by Buddhism. So, that's why he gave this kind of organization of particles this name, eightfold way. So, eightfold way basically is the organization of hadrons into certain geometrical patterns based on this quantum numbers. So, let's see how we are going to arrange hadrons into an eightfold way. So, this is the first one which we call as a baryon octet. So, here we have arranged baryons, and all these baryons, they are spin half. So, all the spin half baryons are arranged in a geometrical pattern, and when we look, we can see that there are 8 baryons arranged here. That's why it is called as an octet. So, this is a baryon octet, and here we have isospin. So, lambda 0 and sigma 0, they have an isospin number 0. Neutron, we have already found it is minus half. Proton, it is plus half. So, according to the isospin quantum number, we have arranged all these particles. And here we have the strangeness quantum number. Again, for neutron and proton, strangeness is 0. For all these particles, strangeness is minus 1. For psi particles, strangeness is minus 2. Now, in this direction, we have charge. This is charge plus 1 for proton and sigma plus. This line is for charge 0. We know all the particles have 0 charge. And this is for charge minus 1. So, this is how we organize baryons, spin half baryons into a geometrical pattern. Now, from this, we can also find their build. What quarks compose all these particles? We are familiar with the quark composition of the particles. So, let's see for neutron. These are all baryons. We know it will be composed of 3 different quarks. And for neutron, we know that a neutron is made up of U, D and D quark. A proton with a U and D quark. Similar calculations will give you the center particles. It is made up of a U, D and an S. Right? This is a D, D and an S. Here this will be D, S, S because the strangeness number is minus 2. So you require 2 strange quarks here. Right? Similarly, you can see here it is, here also the strangeness is 2 and the charge is 0. So it will be U, S, S. This will be U, U, S. Fine. So these are the quark representation of all these particles. Now when we see the quark representation, that also is showing some particular pattern. Right? We're having UDD and UUD. DDS, so center particles, they have UDS, that is one of each quark. So even the quark pattern, the quark combination also follows a particular pattern. So this is how we express a baryon octet, which is meant for particles having spin half. Fine. So now let's move on to mesons. So we have mesons, which forms a nonet. Again, the structure is similar, but we are having 9 different particles organized or classified into this group. So we have the mesons arranged according to their isospin, strangeness quantum number and their charge. So all this have a charge of minus 1. All these have a charge of 0 and this all have a charge plus 1. Fine. Isospin quantum number is there. Strangeness for K particles, they have strangeness quantum number plus 1. Their antiparticles have strangeness quantum number -1, and these are all neutral particles. Again, these are mesons. Mesons are composed of a quark and an antiquark pair as we know it. So let's see how these are made up of. So for K0, we have a strangeness number +1, which means the quark has to be an antiquark. Charge is 0, which means this has to be D. D is -1/3. S bar will be +1/3. So this will give you a K0 particle. Fine. Similarly, this will be a U S bar. Now we have its antiparticles here. K0 and K0 bar. So antiparticle will be having its quarks also inversed. So this will be D bar and S. Similarly, K plus have its antiparticle K minus here. This will be U bar S. So this is a symmetry. So just from this pattern, we can understand the symmetry of the particles and we can find its quark composition. Similarly, here you can find there is no strangeness. So this is charge -2, write it as U bar D. The antiparticle is here, so this will be U D bar. Fine. And at the center, you will be having D D bar, U U bar, and S S bar. All these three cases, all these three combinations, they have strangeness equal to 0 and charge also equal to 0. So this is how we can express all the mesons in terms of their quark composition. Once again, the pattern is really clear. We can use the symmetry operations to find the quark composition of all these particles. Fine. Okay, so from meson knowledge, we are going to another class of baryons. We have a baryon decuplet which deals with baryons of spin 3/2. So there are certain baryons which can exist in two different spins, spin half and spin 3/2. So they are these, the sigma and psi particles. They can exist in two different spins, spin half and spin 3/2. And the spin 3/2 particles, sometimes they are called resonance particles because they are very short-lived. Their energy is high and they are very short-lived. So these are baryons with spin 3/2. Fine. So here again you can see the arrangement based on the isospin, strangeness and charge. So we are introducing a new particle. This is called delta particle, which are baryons but not strange particles. So delta particles, there is a delta minus, delta 0, delta plus and delta plus plus. So we are having charges -1 along this line. Along this line it is 0. Along this line it is +1 and here it is +2. So these are the different particles that we have in this baryon decuplet. So the name decuplet comes from 10. So we are arranged 10 particles in this organization. So once again, when we look at their quark composition, we can see that here the charge is -1, strangeness is 0. This will be composed of D, D, D. So this is a baryon. Baryons are composed of 3 different quarks. Again, if you need a charge of +2, this must be composed of U, U and U. Then only you will get a charge +2. 2/3 plus 2/3 plus 2/3E. So you'll get a charge +2. Now here we have our omega minus. Omega minus is having a strangeness number -3, which means that this must be composed of 3 S quarks. So once again we can see that beauty. At one end we have 3 D quark, 3 U quark and 3 S quarks. Now we can just fill all those things. This will be DDU, DUU. You can just work out the math and you can find that all these particles will be composed of these quarks. Okay. Similarly, sigma minus, this will be DDS because the strangeness number is -1. When you come to psi, the strangeness is -2, so this will be DSS and then you have SSS. Similarly here, it will be UUS, USS and SSS. So it is evident from this pattern that the center particle will be having UDS quarks. So here you can see that symmetry, the symmetry property of all these particles. Right. Now, actually, when Gelman proposed this method, at that time, only the particles up to here were actually discovered. When he formulated this eightfold path, only these 9 particles were discovered, but he predicted the existence of a particle with 3 s quarks based on this diagram. So, it was predicted in, I think, 1962, and 2 years after the prediction, the particle with the same properties as predicted were discovered. So, that is what the advantage of having an organization, a pattern like this, where we can classify baryons in terms of their isospin, strangeness, and charge. So all these particles are now discovered. But we know there are a lot of subatomic particles, like hundreds and hundreds of subatomic particles already existing and yet to be discovered. So one, I don't know whether it is latest, but Fermi Energy Lab, they have a similar structure, an organization of particles. And out of all these particles, only 2, this and this, has been discovered yet. All other particles, they are only just predictions. So this set of particles, they all have B, which means this is a bottom quark. So till now we have been dealing with up, down and strange quarks. Now there are other particles also which are composed of charm quark, bottom quark, top quark. So this is a set of particles which are made up of B quarks. And all these particles are only prediction. We know that all these red particles, these have all been discovered. We have seen it in the previous slide. And among this generation, these 2 particles have been discovered as of now. But the structure predicts the existence of all these other particles. So there are hundreds of particles which are yet to be discovered. So this kind of an arrangement is exactly similar to the periodic table that we see in chemistry. So when Mendeleev discovered the periodic table, most of the elements were missing at that time. But he could predict the properties of those elements based on that arrangement. He arranged all the known elements based on their properties and he could predict the missing elements. Similar way, once you construct a pattern like this with the hadrons that we already know, we will be able to predict the existence of new hadrons. And now the particle physicists know what to look for because these are all already predicted. So when they do experiments, they can look for these kind of particles. So it is easy for discovering them. So this is the main advantage of having this eightfold way in particle physics. It will give you enlightenment about all those fundamental particles that make us. And it will also give you, again, an advantage in looking for what to be discovered. It will give you some particles. We know they are present, they are theoretically existing, and it's just a matter of time to get discovered experimentally. So this will give us a small brief about elementary particle physics. We have seen different classification of particles, the composition of particles, that is quarks, and also how we can organize them in particular geometric pattern and learn more about their properties and the existence of even new particles in our universe. So that's all for the session. Thank you.